pick it up where we left off.
Alright, so last thing your notes is about the vessel radius, how it affects the resistance to blood flow. And so that'll be the first thing I talk about, the sympathetic response of arterioles and how it increases BP. Arterioles have sympathetic innervation. Now that's not the nervous system that's usually on. Usually it's parasympathetic that's on. So at the left, that's the default physiology you should know. The parasympathetic is on. Which is our default mode. You block sympathetic. That allows the tunica media to vasodilate, and that will lower blood pressure. So I'll put VD, vasodilate, drop BP. So that's on the left. So on the right, it's the same thing in reverse. If you turn the parasympathetic off because of the fight or flight response, what you're doing is you're removing the sympathetic block. Remove SYM block. So as you can see, you increase the firing. You increase, we call it tone. You're just firing more neurotransmitter. Increase sympathetic tone. I liken it to just turning up the volume knob on your stereo. Whereas the top one is turn down the volume knob, just block it, turn it down. There's it, turn it up. You vasoconstrict and you increase blood pressure. Okay, so that's the basic idea there. Teaching students how constriction or dilation can affect systemic blood pressure. So I'll put some half sheets out there. If you didn't grab one, grab it now and answer this question. Let's call this, I don't know. How about number 1? I have 1, 2, 1, 2, but let's call this number 1. And you're going to put two things, blank and then blank. For the first blank, you're going to choose from one of these. And then for the second blank, as a result, it causes an increase or decrease in BP. Okay, so that's the basic. I can't make any more basic than that. So choose the correct line of thinking. Which causes, when you have a sympathetic nervous system response, what's the effect? Okay, based on what we just talked about. So for number 1, it's sympathetic. For number 2, it's going to be parasympathetic. Right, for number 2, there's 3 blanks. If you turn on the parasympathetic nerves, what's the effect on blah, 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 just read it. I just choose from one of these, then choose from one of these that happens, and choose from one of these. So I'm trying to get you thinking about the process of how blood pressure is affected. Fill in those 3 blanks when the parasympathetic is on. And we'll move on. All right, let me check on this second one. Turn on the parasympathetic. Which did you choose? Yeah, you should have chose this one, because what did I just say? When it's on, you block it, which is the same thing as inhibition. So if you block this sympathetic, which is more likely to happen? Vasodilate. When you vasodilate, what's more likely to happen? Drop in blood pressure. So in our lab, when your subject was lying on the ground, usually that's the effect that we want to take place. Okay. Well, let's move on. That's the basic idea. We'll come back to this idea of constriction and dilation. So the why behind constriction increases the resistance to blood flow. You first need to understand what's happening to blood flow through a tube. This could pertain to any liquid flowing through a tube. This is the figure that's usually given. Oh. So in this scenario, they have a tube. You assume it's a blood vessel. But right down the central axis, what physicists will tell you, imagine all the blood as being divided into layers. The innermost layer has the fastest velocity of flow, shown by the arrow. Well, it's a red arrow right in the middle. It's the longest one. I know you haven't had physics, but usually the length of the arrow means faster in that direction. Okay. But as you go in concentric circles around the fastest layer, what you're doing is you're getting closer and closer to the vessel wall, which they call layer 0. And the layers closest to the vessel wall have the most friction. More friction. And what I say about friction is more resistance to blood flow. So their velocity is slower. But the layers further away are faster. So I mean that's kind of why you have that shape. I mean that's the idea. So the reason why vasoconstriction increases a resistance for blood to flow is because in B, you're vasoconstricted, you have proportionally less layers with that nice laminar flow with no friction against the vessel wall. But when you're dilated, you proportionally have more layers far away from the friction of the vessel wall. So you're supposed to have less resistance to blood flow. So, I mean, so in physiology terms, when you're constricted at the arterial level, you increase the systemic blood pressure. I mean, that's what we're supposed to measure when you get a sympathetic response. Now, I want you to start thinking about lab on Friday when we have our BP lab. How do you elicit a sympathetic fight or flight response? One way you could do it is pain, a noxious stimuli. And the typical thing that's done is cold pressure test, where a student will submerge their hand into icy cold water, which is very painful. And you submerge it for a period of 3 minutes. And that pain is supposed to cause a sympathetic response to increase blood pressure. So we'll get a chance to do that on Friday. I don't know if you remember writing this on the board. Remember that from last? It was like the end of the lecture, you're tired, maybe you wrote it down. You haven't studied your notes yet. What's little r?
Radius.
Vessel radius, very good, you guys are on it. And the fact that it's to the 4th power means, you change the caliber of the vessel, you dramatically can increase or decrease the resistance to blood flow. So this is the typical thing I usually show students. It's straight from physiology textbook. All other things being equal, just alter the radius a little bit, go from 5 to 4.2 millimeters, you affect the flow by half. The flow rate, I should say. By reducing vessel radius by 16%, you decrease flow by half. So that's basically an example of that. You change radius a little, you affect resistance a lot. You've reduced it by half. Okay. So let's kind of talk about that conceptually, this arteriolar constriction in a couple of different ways, systemically and locally. Let's remember that the arteries have branchings from elastic to muscular, and then the smallest arteries are arterioles that feed the capillary beds. But you cannot distribute all the blood everywhere all the time, so you kind of only make it flow to where it's needed, and you kind of shut it off where it's not needed. And so how the body decides to do that, I mean, it's not something you think about, it's completely automatic. So we call that a localized intrinsic autoregulatory mechanism. These are the kind of the adjectives I notice most textbooks like to use. So I try to use them in my lecture. Localized means not the whole body, just a very small part. Maybe a part of my shoulder, okay? A very small part of the body. Intrinsic. Intrinsic means it just self-regulates within itself. It doesn't take some outside hormone or nerve to make it do it. It's all in-house. Autoregulatory means automatic, it just does it all by itself. And what are we regulating? Arteriolar constriction. Localized intrinsic mechanism of arteriolar constriction. So it's like if you have a blood vessel, we use red for arteries. And a small arteriole comes off of that. Say blood flow is this way. The goal of blood flow is to prevent ischemia. So you constrict or dilate based on how much blood flow you need. Okay, you just want to make sure the tissues don't become ischemic, which means a lack of blood flow. So if you have if you have plenty of O2, say in cells of a region, the capillaries that supply blood to those cells, if you have plenty, you can constrict, you can turn it off. Okay? You can, I'll just like go like this. I'll draw like a little constriction event there. Right there. Because you got plenty of O2, let's just turn this off and divert the blood somewhere else. Okay? You decrease radius, but you're increasing the overall resistance to blood flow here because you don't really need it. But let's say O2 levels start to drop off. Now these start to like need oxygen for their metabolism. So there's a lot of metabolites that build up within the blood vessel that signal it to dilate. And there's a figure in your book that kind of lists them all. You know what, I'm staring at the book right there. Let me see if I can find the figure that I'm referring to. Chapter 19. Yeah, that figure's kind of changed it a little bit. But the figure that's good to look at, that's kind of like this one, is 19.4 in the newest edition. That's kind of like what I'm trying to draw here. It's a good one to look at. The figure I was talking about with all those metabolites, I think they dropped it. Maybe they thought it was lame like I did. They realized it was too much. But I looked at that figure, I'm like, you know, there's one metabolite that's really important that drives vasodilation when things get hypoxic, and that's nitric oxide, and I mentioned that before, so know that one. When things become hypoxic, a lack of blood flow, let me define these words. So a lack of blood flow, usually the word that's used is ischemic. But what does that ultimately cause? A lack of oxygen. And the word that's used for that is hypoxic. So know those words. Tissues become hypoxic, lack of O2. So you need to restore the blood flow. So then nitric oxide increases within the endothelium. And that'll help you vasodilate. So NO from endothelium accumulates. So that causes VD, vasodilation, that restores blood flow and oxygen. I'll just say restores flow. And so the ability of this constriction dilation it's all self-regulated. Okay, you just go back and forth between this or that, depending on the tissue's needs. Now this one is a nervous system response. Widespread. What I really mean is it's systemic. It's happening in your whole body because blood vessels go everywhere, the whole system. Extrinsic, because it's a sympathetic response, SYM. So sympathetic efferents are going to innervate blood vessels. So the sympathetic mechanism that I just talked about. So in the lab, it's the cold pressure test. You know, what happens when you're under a lot of pain? What happens when you're really scared and fight or flight response? What does that do? So what happens is, systemically, you know, you have a large group of blood vessels. So I'll draw three to represent a large group. These will supply blood to big parts of your digestive system, like GI tract and liver, your intestines and liver. I'll just say GI tract, gastrointestinal tract, and liver. During a fight or flight response, you don't need digestion. So you just kind of like widespread, you just kind of, there's a sympathetic efferent. You just fire, you clamp down on the arterioles that supply blood to these parts of your body. And I'll just kind of draw these clamped off. Decrease little r, increase capital R. What you're doing is you're diverting blood to a smaller group of arterioles that actually vasodilate. So I'll draw the rest of this system. There's a smaller group. I'll just draw one. So blood flow, it can't, there's no blood, there's very little blood flow here. So it's like you're keeping more blood in the arterial system. And if you were to measure the blood pressure, you would measure an increase in blood pressure during this response. So in the cold pressure test, I would say after the first minute, when you get your first reading, you might see an elevated blood pressure compared to baseline. So what happens is this blood is diverted to a smaller group of arterioles, which will actually vasodilate, not vasoconstrict. So I'll draw this vessel dilated. You increase the radius, you decrease the resistance to blood flow. You're going to increase capital F blood flow to a smaller group, and it's usually the skeletal muscle, the working muscle beds. That's kind of how they're called. So it's a larger group, that's a smaller group, that's kind of what's happening. I mean, it makes sense to me. It's like your whole body is like mobilized to just respond to the stress, whatever's causing it. So that's kind of what I write here. You have a vasoconstrictor response very well to GI tract and liver. The sympathetic inputs to working muscle beds, they actually work in reverse. It's a vasodilator response. It's a smaller group. Overall, you're monitoring an increase in blood pressure. Okay. All right, so any questions on that? Because now I'm going to shift gears and talk about the sympathetic response to veins.
When you talk about the localized and the intrinsic, is that nitric oxide a waste product from the endothelial cells?
No, it's not a waste product. It's actually, the cell physiology is there's a second messenger called cyclic GMP, which is produced to make that. And so it's not a waste product. It used to be called endothelial derived factor. They didn't know what it was. And once they figured it out, they said, okay, now we're in business. Actually very important. Well, I talked about it in terms of erectile dysfunction. Remember that?
Yes.
Yeah, that's the basis behind that. It's also a risk factor in heart disease. If you don't have that, you have more risk for heart disease. Why? What is heart disease? Lack of blood flow to the myocardium. Now, when I studied heart disease as a grad student, that was extremely important. Nitric oxide was talked about a lot. All right, so the venules in the small veins, okay, what's their sympathetic response? I kind of put this in because I showed you this picture before, and they show the arteries smaller and the veins a lot bigger. What the veins do is they decrease the radius a little bit over a large area. So let me see if I can do like this. So I just got talking about the arterial constriction. Okay, so they basically squeeze in one part, like really a lot, like right there. Just really clamp down. So that way, you really increase the overall resistance when you really clamp down in one location. What I'm saying for veins is, venules, small veins, it's different. So they're much larger. But you don't clamp down in one spot. It's like you take the whole thing and you just kind of decrease the radius a little bit. So you have a slight decrease in the radius, little r. But it's so slight, you actually don't affect the overall resistance. So, no effect on capital R overall resistance. What you are affecting is you're decreasing, because it's over a wider area, not just one part you're squeezing on. You're taking the whole tube and you're shrinking it. You're affecting the capacitance. You're shrinking the entire container. What you really affect is you decrease capacitance of your capacitance vessels. And because you're making the whole container smaller, you're increasing the venous pressures, which are low to begin with, so increase venous pressures. When you do that, you're going to increase venous return. And because of the Frank-Starling laws, more in, more out, you increase cardiac output. CO. When you increase cardiac output, well, don't you increase blood pressure? You do. So all of that train of thought, they call that the mobilization of the blood reservoir. Well, I remember as a student, I was confused about this. Because I remember learning, going over my lecture notes just like you guys do, okay, so I was like, oh, so you decrease the radius, you increase the resistance, and I understood that. But then, when my professor mentioned this, like it didn't make sense to me. Wait, how come you don't affect that? And he gave me this example, like where you like, if you had a garden hose, you ever had a kink in your garden hose? And you turn on the water and water doesn't come out? That's this. But then he's like, well, don't do that. Just take the whole garden hose and just shrink it just a little bit. Okay? Or even like in your mind, picture you squeeze a little bit on the garden hose. What happens to the water flow? Does it stop? It actually increases. Okay, you know. So I think that's what he was trying to explain to me in office hours. This thing. You have any questions on this? Think about this. Slight change in radius. You don't affect resistance. What do you affect? capacitance, how much it can hold. Increased pressure, increased return, increased cardiac output, increased BP. Okay. What you're doing is you're increasing the inflow by increasing the cardiac output. You're increasing the inflow of blood into the arteries. That's why they call it mobilization of the blood reservoir. Where did I say most of your blood sits? In the veins. So if you want to get it to the arteries, do this, which is desirable for a sympathetic response. Over here, you're doing the opposite. You're not increasing the inflow, you're decreasing the outflow. You're preventing it from getting to the capillaries. So, right here, if you decrease the outflow here and increase the inflow there, you're going to see an increase in blood pressure. So for you in lab, minute 1 and minute 2 of the cold pressure test, the painful stimulus should elicit some kind of response. Okay. Well, let me read what I have on my slide. So you took notes on this, but then read the slide too. I wrote this as well. It's a sympathetic stimulation of venules and veins. They generate a small constriction over a large area, right? Over the entire length of most of the venules. So the change in radius affects capacitance venules and small veins with no effect on resistance to flow. Changes in capacitance rather than resistance occur because of the large cross-sectional area effect. Again, it's not just one little part you're squishing, it's the whole tube. Or you're shrinking it just a little bit. Here's a picture of that. So they show the sympathetics being affected over a larger area. So this whole tube is shrunk just a little bit. It's definitely affecting both sides of the circulatory system, the arterioles and the veins there. Okay, so let's start to summarize. We have a lot of notes, and I tried to distill it down to 1, 2, 3, 4. Okay, 4 is the goal. 4 was the whole point of this lecture, that students understand how the body maintains the blood pressure, the mean arterial pressure. So write that down. This equation is in the write-up of your blood pressure lab. Blood pressure, conceptually, is determined by the cardiac output and the resistance. So as a student, everything we talk about, boil it down. Am I affecting cardiac output or the resistance to blood flow? Okay, this peripheral resistance. So, number 1, cardiac output, that's my inflow. If you increase cardiac output, how do you think you affect the blood pressure? Up or down? Up. So that's the general relationship. This causes that. Okay. And the cardiac output and the resistance, they usually go hand in hand. They operate together to accomplish the same task. What would increase blood pressure? An increase or decrease in resistance? That's our outflow. If you increase the resistance, you're going to increase the blood pressure, because if you kind of pinch down more here, you're keeping more blood in the arteries, so that helps to increase blood pressure. So that's the general relationship. This goes up, that goes up, the blood pressure goes up. So these things cause the blood pressure. All right, so now let's begin to talk about how we affect R. This, think of the arterioles. What do the arterioles do to their radius to increase the resistance to blood flow? They vasoconstrict it, they decreased it. So that is the cause of the resistance increasing to increased blood pressure. The thing I just talked about, the veins, I'm going to put them under here. That's the thing where you decrease radius, but it was very slight. Decrease R slight. You don't affect capital R resistance. You decrease capacitance. You increase the venous return. More in, more out. That helped increase the cardiac output. So that helped boost your blood pressure. Okay? Let's think about the heart itself. For the heart itself, what do you think happens to heart rate to increase the cardiac output? Up or down? That one's easy. Increase. Excellent. What about stroke volume? Because heart rate's a product of the rate and the stroke volume. Cardiac output is a product of heart rate and stroke volume. Stroke volume also increases. Okay. And let's just say overall contractility increases too. These are all the things we talked about for the heart. So I want to write contractility. Contractility, that also increases. Increased heart rate, increased contractility. So all those things are happening to affect cardiac output to increase the blood pressure. But here's another way I put it. Here's that equation there. And what I did was I just put cardiac output, resistance, and blood pressure. So these are kind of the things I try to steer students to just think about just that. Now we're going to come back to this equation when I talk about the baroreceptor reflex. Now I'm going to move on to another topic unless there's any questions on that. Basically, number 1 and number 2 cause 3. But for number 1, you have to think about these determinants. And for number 2, you have to think about these determinants for arterioles. Now, veins in general have very low pressures. So when there's not a sympathetic nervous system going on, the book has outlined modifications to maintain venous return. How is all the blood returned to the right heart when venous pressures are so low? Large lumens, venous valves, and 2 venous pumps are modifications or compensations to accomplish venous return because there's no venous pressures. So we put that on the board. Let me phrase that in the form of a question. How do veins accomplish venous return to the heart, you should know that, with no pressure. Because I keep talking about arteries, how arteries have high blood pressure to push it to the capillaries, then you get your capillary exchange, and then the veins are the collection and return system, but there's no pressure in them because they're too far away from the heart. So what are some of these compensations that veins have? Well, the first thing is they have larger lumens in arteries. So you have decreased resistance to blood flow. There's more layers of blood flowing that has that nice laminar flow with no friction against the vessel wall. So that's one compensation. They're larger. Number two, venous valves. They have venous valves throughout their length. The arteries don't. They just have the semilunar valve at the beginning of the heart, and there's no valves after that. So what this shows you is what fluid flow is like. First, with no valves. If you squeeze a tube filled with fluid, you squeeze the fluid in both directions, up and down. Over here, skip to C. But if you have semilunar valves, say you're standing up, at least blood doesn't flow backwards because all the semilunar valves close. This shows what venous valves do in conjunction with a skeletal muscle pump. If you have blood in this middle compartment, if you squeeze, it's prevented from going down, and you only squeeze up towards the heart. Okay. So venous valves, working with something that's called a skeletal muscle pump. Move blood back towards the right heart. So if you keep your steps up, during the day, it's fine. You do worry about this in patients who are confined to bed for long periods of time. So that's it there. Now, this next slide just kind of shows you the skeletal muscle pump in more detail. This first slide shows you that when the muscle is relaxed before it contracts, you're allowing fluid into this compartment here. So when you squeeze, you only move it in one direction. And then after the muscle relaxes, you allow it to refill. Okay, so walking around, when I say you're on a long plane flight, it helps increase the circulation. Question?
So if you're trying to prevent, like, what's the word, blood blocking, or like, how they put restrictions on your legs and your arms to prevent blockage from blood clots. Yeah, sorry. Are they focusing on the venous valves? Is that
Yeah,
okay.
They're focusing on this. They're trying to, I believe, I don't know what they're called, what you're talking about, but I know what they do. I think they vibrate or contract.
Yeah.
They're trying to simulate this because, for whatever reason, you're immobile. So it's like they're doing it for you.
It's not the other ones then. It's not the atrials then. I was thinking because those guys are harder.
It's not the
Yeah.
No, the arteries have the heart. It's the vein. It's the blood in the veins you're trying to help.
Okay.
Yeah, it's the venous return that you're aiding. anyone know what those are called? Those things they put on your extremities that vibrate or contract.
They call them scuttles.
Scuttles?
Scuttles.
Do you know what they're called, Veronica?
They call them scuds.
Scuds. Okay. Do they exert pressure or do they just vibrate?
They like rough. It's kind of like a blood pressure cuff on your face.
Okay. So they actually.
Yeah, it has a timer on it.
Yeah. Okay. You know how often they, the frequency of them going off, like every 10 minutes or
They
something?
can have it on all night.
Okay.
Or like during the day and then turn it off a couple hours later.
Okay.
You know, I had it when I was pregnant.
Oh, you did?
So I had it on the whole night.
The whole night. Okay.
Yeah.
Good. Yeah, so my understanding is they're helping the venous return. This helps venous return too. This is another pump. They call this the respiratory pump. This is your natural breathing. Scuttles. Now the respiratory pump is basically, okay, think about when you breathe, doesn't your chest cavity expand? So you're increasing the volume of your chest cavity, your thoracic cavity. When you increase the volume, you decrease the pressure. So that's why, well, first of all, this person is laying supine. So that way you eliminate the hydrostatic pressure. Second of all, take nice deep breaths. And with the respiratory activity of breathing, you're creating a little less than atmospheric pressure in the chest region. Everywhere else, it's atmospheric pressure, okay? They call that pressure on the body surface, but they just show the veins. And so you create a little bit of a pressure gradient, sucking blood back to the heart. They call that the respiratory pump. Inspiration, that's breathing in. Causes slight negative pressure. Relative to atmospheric pressure. Creates a slight gradient for blood to flow back to the heart. For flow back to the heart. Got some practice questions in here. These are good to look at after you've studied. They're throughout the entire lecture. We talked about all of that. I don't want to take time to talk about it now, but I just wanted to bring it to your attention. These are good things to look at after you've studied this lecture. Okay. The next batch of slides I want to talk about are the baroreceptor reflex, and that's the reflex that's the focus of Friday's lab. So I wanted to be sure that I cover that today, so let's start that. Baroreceptor reflex. These slides. These are good to do in lab because reflexes, they happen really fast over the course of minutes, so students are able to observe their effects really quick in the terms of the short-term time we have in our lab, a couple few hours. First of all, I wanted to start with, now that we've learned about the basic idea of how blood pressure is accomplished in the body, let me show you a slide showing you hemorrhagic shock. Basically bleeding. Shock is a loss of blood. And so look on the x-axis, they say percentage of total blood removed. Okay. Now on the y-axis, they have cardiac output and arterial pressure, percent of normal. So you see, this is why we keep talking about the arterial pressure. It's the one you want to monitor. So you're bleeding out. And the time course for these data is about 30 minutes. Okay. So some trauma, you're losing blood. The first thing I want you to notice is what's called the first plateau for arterial pressure. You start losing blood at 0. But look at arterial pressure. Does it drop off? No, it doesn't. You keep going and you're losing blood, you're losing blood, you're losing blood, and it keeps maintaining. So that's blood loss for about the first 20%. From 10 to 20%, there's no change in arterial pressure. So this is the value of what we just talked about, those sympathetic reflexes. Why? Sympathetic reflexes. Your body is very well attuned, very well adapted to maintain blood pressure while you're losing blood. So, number one, what did we say? The arteriolar constriction, vasoconstriction of the arterioles. Vasoconstriction of arterioles. That's the one where you dramatically increase the resistance to blood flow. You keep blood in the arteries. You don't let it escape to the capillaries veins as much. Second thing, vasoconstriction of veins. I said you don't do that. You decrease capacitance. I say cap for short, I'm running out of room here. And that whole thing, you increase venous return, increase cardiac output. Increase VR, venous return, increase CO, cardiac output. And then the third thing, you affect the heart itself. Increase heart rate, increase contractility. So those three things allow, the body to maintain blood pressure when you're losing blood. Now, how much is 20% of your blood? What's the average blood volume? 5 liters. So what's 20% of 5? Mm-hmm. How much is this? Half liter. So, people always say, I've always heard people say, oh, you've lost a lot of blood. I've always wondered what that meant. What's a lot of blood? Well, according to these data, 20% is. Because after 20%, your pressure starts to drop. So imagine 2 of these full of blood. Let's say you're a first responder, you arrive at the scene. If it looks like 2 of these are like all over the place, that's a lot of blood. Because you can assume shock is going to happen. All right, so then blood pressure starts to plummet. That person is probably not conscious. The blood pressure is dropping. When it gets to here, they call this the second plateau, around 40%. Well, at this point, well, before this point, these sympathetic reflexes, you're always pumping blood to your vital organs, basically brain, heart, and lungs. But if pressure drops too much, even your vital organs become ischemic. So at 40%, the brain is becoming ischemic. And so then the brain is like, oh, okay, let's supercharge these sympathetic reflexes to try to keep me alive, you know. Over stim these sympathetic reflexes. That's kind of like the last ditch effort. But of course, if blood loss continues, well, shock will ensue. Okay. You can help. You can put pressure on the wound up a little bit. You can use tourniquets. Tourniquets can help. You know, a lot of times I walk around with those medical grade tourniquets. I should show you those. Those are cool. They can really save someone's life. I'll talk more about tourniquets later. Okay, maintaining arterial pressure. In terms of how the body does it, there's short-term, long-term. I'm focusing on the short-term today because that's the reflex response I want to talk about. That's our lab on Friday. The longer-term one, they help maintain the blood volume. Do you remember studying all those hormones where I kept saying increased water reabsorption, increased blood volume, increased blood pressure, that whole thing from the first test? That's this. So I'm not going to focus on that too much. So basically, how I teach this is, for the short-term neural responses, our reflex, we're going to see how that can change blood pressure. Over longer terms, say days, weeks, months, the body does it with hormones by regulating blood volume. So for that second point, the hormonal controls, which you're still responsible to know for this exam, lecture exam 4, I just made a table for you. So make a note to yourself to review these hormones. The FA, norepi of the adrenal medulla, atrial natriuretic peptide, ADH, EPO, and the RAS mechanism. Okay, so this first one, this is actually part of the fight or flight response, where you increase cardiac output and peripheral resistance to increase blood pressure. This is the only one that can drop blood volume and blood pressure, A and P. All the rest of these act by increasing blood volume, increasing blood pressure. So I don't know if you remember writing about the RAS mechanism. Maybe if you don't remember writing about it because maybe you didn't do it. I don't know. But I think you're still responsible for it. I won't have you write about it, but I will create multiple choice questions about that. So I put review question mark because if you've forgotten that mechanism, go back and look at it. There may be a question on the next exam. All right. So this reflex involves understanding this equation, which we just talked about. And I want to make sure that we all remember what a reflex includes. Some kind of way to detect the error, a receptor. Afferent pathways. So we'll talk about the nerves that take the signal from the receptor to the brain. And then we'll talk about the control center, the brain itself, where you're comparing some signal to a set point. You process the information and you generate the appropriate response. So then you have to talk about the efferent nerves, or the motor pathways, to affect the correct organs or structures to restore homeostasis. I mean, so for us, I just kind of made this slide for you. We're going to talk about the baroreceptor, how it affects blood pressure. So the baroreceptor, like a barometer detects atmospheric pressure. This is the blood pressure. And then so I just kind of outlined everything here. And the picture you should study to go along with this is right here. So for our lab, what we're going to do is, in your subject, we'll increase the blood pressure and we'll decrease the blood pressure. And we'll monitor everything. So this time we'll monitor pulse and we'll have BP cuffs out so you can have an opportunity to listen to the blood flow sounds to monitor blood pressure. So I'll teach you all that later. But for now, just the concept of the reflex. This is the cold pressure test. When you have a reflex, that means you're trying to correct something. In this case, blood pressure will get too high or blood pressure will get too low. So this is the too high imbalance. All right, so, okay, you're trying to regulate BP. Good old 93, 120 over 80, your normal blood pressure. But some stimulus, like cold pressure tests, pain is not your friend. Pain makes everything out of whack. So you have a jump in blood pressure. And whenever I do this, I always tell students, write somewhere, you know, okay, this is the imbalance, what do I want to do? I want to decrease blood pressure. You want to drop BP. I always write that down just for myself, so as I go through it, I don't get lost in the details. I always anchor myself to this is what I want to accomplish. So for this, if this is the imbalance, you go to the baroreceptor. Now, I told you where these were before. Let me remind you. Here, carotid sinus and aortic arch. Those are two locations. Close to the heart. Carotid sinus, aortic arch. You get to the baroreceptor. Okay, what happens is, if you have a jump in blood pressure, can you imagine that you're increasing the transmural pressure because of the jump in blood pressure? Increase P-trans. Increase stretch. Turns out, these baroreceptors are stretch sensitive. You stretch them, they fire more. So maybe nice, relaxed, you're spaced out, action potentials, but then painful stimulus, cold pressure test, you fire more. So you're going to send more action potentials to the brain. That's our afferent. I want to put increased APs. It's going to be impulses from baroreceptors from here to here. One of them is cranial nerve 9. 9. That's carrying the afferent signal to your brain. In this case, it's going to be the medulla. It doesn't say medulla here. Okay, the medulla is just part of the brain stem. Now the medulla has in it a cardiovascular center that can help mobilize the correct response. It's going to compare the incoming signal, more APs, and it's going to mobilize the correct output. Cardiovascular center. Now, there are 3 centers within there that help control heart and blood vessels. And they're listed here. Cardio inhibitory, cardio acceleratory, and the vasomotor center. So you got cardio inhibitory, cardio acceleratory, and then vasomotor. Okay, think of these as 3 subcenters in this cardiovascular center. Okay, so it's receiving the input, more APs, right? More action potentials. And it's like, okay, this is where I look at my note, my cheat note. Blood pressure's too high, I want to lower it. So what will accomplish that? Yeah, let's turn on this one, cardio inhib. Let's get my heart to try to slow down. It's beating too fast. Let's turn off those other two. The vasomotor, that's sympathetic response to your arterioles and stuff. We don't want that. Turn it off, turn it off. So this is the thing where I said earlier in the lecture, turn on parasympathetic, you know, you want to block the sympathetic. Turn on parasympathetic, block sympathetic. And that's kind of what we're doing here. So when you do that, in terms of these two, heart, you're decreasing the heart rate, you're decreasing the contractility. And for the vasomotor center, you're decreasing that sympathetic tone we talked about. So when you do that, you, so here's a blood vessel and arterial. I guess you vasodilate it. Or you go from there to there. I'll put just VD, vasodilate. So where we're going is the whole, think about resistance and cardiac output. Decrease resistance, decrease cardiac output. So I always like to end by saying, think about your equation. Blood pressure as a result of cardiac output and resistance. You're decreasing both of those things, so you decrease blood pressure. So hopefully you did it right. You know, if you increase it, then you decrease it as a result. So again, this is the cold pressor test. In your cold pressure test, you should observe a rise in blood pressure followed by a drop in blood pressure. Now, we don't always observe that when we do it in the lab. Usually we just observe a rise in blood pressure and maybe it never goes down. And that's okay, but know that that's what should happen given enough time. Let's take a break and we'll come back and we'll talk about the other part of the imbalance. Come back at 9 o'clock. Should be enough time.